Okay, so today we'll be talking about isoelectric focusing. This is a very important lab technique that's also technically under PAGE because it uses a polyacrylamide gel, but it differs for reasons we'll just go over. So let's always start with a motivation. Suppose we have protein A. All right, let's say protein A, and this protein A, let's say, plays a very important role in the cell. Let's say some sort of kinase or something, right? And we need to know whether or not he is phosphorylated or not. Let's just say, big difference if he's phosphorylated versus, when A is not, right? And how do we know this? How can we even figure this out? Well, phosphates have a negative charge, right? And in this case, we wouldn't really be able to use any of the PAGE techniques we've already known because the addition of one phosphate makes very little difference, right, in terms of size, especially. So we need a way to somehow be able to sort this out by charge, right? Because phosphates, they have a pretty strong charge comparatively to the effect on its mass. So we basically want to rule out the mass because these two masses are very similar, whereas the charge differs quite a bit. Unless the protein itself is very heavily charged, in which case it might be more difficult, but this is probably the best way, right? We want to figure out the charge of the differences of these two proteins. And let's say we have two proteins, right? But we don't know if they're related or not. If we dephosphorylate one of them and they end up being the same charge, then we can probably be sure that they're the same protein, right? Like imagine we had one protein that was charged, let's say -3, and the other one was charged 5. If we dephosphorylated this guy and he led to let's say his new charge was 5, right? Then we would know they're probably the same protein. So that's also another potential use. So we want to be able to sort proteins by charge, in other words. And we do this using isoelectric focusing, where we actually use a pH gradient. Now, pH gradient, what exactly is that? So let's take a look. If we have a polyacrylamide gel, right? We have a gel right there. What we can do, or what we want to do, is basically have different sections. Let's say this is the anode, this is the cathode, right? We want to have sections of this where there are different pHs, right? And let's say this is pH like, let's say this is pH 2, let's say this is pH 3, and it goes all the way to like pH 10 or something, for example. And if you recall, proteins are amino acids, right? And amino acids, let's draw the structure right now. There's a carboxylic acid, right? We have our central carbon. We have just hydrogen chilling there, a side chain, and the amide, right? Let's draw them in this form. Remember that each amino acid has multiple different forms, right? Because we have 2 acids on each amino acid at least, right? Sometimes we might only have 2, sometimes we might have more, but at least we have 2, and that's the amide group and the carboxylic acid, right? If you remember from when we talked about the stacking gel and how we use the isoelectric point of glycine, right, between the stacking gel and resolving gel to change its behavior, exact same thing here, because here in the middle, right, at a certain pH, it'll differ for every protein, right? But we'll have one where the carboxylic acid gives up its hydrogen, it deprotonates, right? And now we're left with a neutral ion. We call it a Zwitter ion, right? And then this again, let me just move over here. This again can depronate again at high pHs, right? So this says low pH, like medium pH. Obviously medium is very subjective here, right? And then at high pH, what we'll have is that this amide will also depronate, right? This should be an R. This should just be simple acid-base chemistry, right? Here we go, NH2, right? And so this is negative, right? Neutral. What's the sign for neutral? Okay, just yeah. And then this is positive, right? And so we see that at different pHs, different proteins, right, assuming they differ in charge, will go to different places because of this property, because of, well, acid-base chemistry, right? So this is sort of what we want to do, and let's just go over the mechanism of exactly how we set up this pH gradient and how we're able to utilize isoelectric points of proteins to figure out what the hell is going on, yeah? So let's go over the mechanism. First, let's do creating the pH gradient. Sorry, this is meant to say gradient. Creating the pH gradient. So what we have are amphilites, right? And amphilites are basically just any like molecule that can act either as an acid or base, right? And these, let's say we have thousands of them, right? Have differing PIs, which are just isoelectric points. So imagine we have an acrylamide gel, anode, cathode, right? And we put a bunch of these guys, let's say either over here or in the middle, right? It's just a bunch of these amphilites, sorry. And then we run the current. Let's say we have current, right? And we have our battery, right? There's our circuit. And let's run it. They're gonna sort based on their isoelectric points, right? Because think about it, amphilites would have the exact same thing that we just talked about. They're gonna go to where, like when they're positive, they're gonna move away, right? Let's say the thing is positive, it goes towards the negative cathode, right? And at a certain point, it's gonna depronate that ion. It's gonna be like, I don't want the ion anymore, right? And then, boom, we're gonna have him, let's say over here. And likewise, the other way around is gonna go over that way. And then they set the pH in that local region as well. So that's also very important. And now basically what we have after we've run this for a while, we've basically made ourselves a gel that has different pHs, right? At certain pHs, these amphilites will take back the H's or give H's, depending on where it is, to the protein that we want, right? And so that's basically where the pH comes from. And so this whole technique is called electrofocusing, all right? And just basically, if you're going to have any takeaway, we're just making a pH gradient. So now we're left with, a gel with different pHs. Maybe this pH is pH 2, and then this pH is pH 3, this pH is pH 4, right? That's all we care about, because they're going to go in ascending order. And at the positive anode, it's going to be a lower pH. At the negative cathode, it's going to be a higher pH. Why? Well, at a lower pH, the proteins, if we go back, are going to be in this positive form. And we want the positive form to go to the right? We want it to go this way. So that's why we position the anode at the low pH side. Okay, so now what do we do? After we have this, right? Now we place our proteins in the middle. All right, let's put a bunch of proteins. Let's say these red dots are proteins. I don't know if you can see that, actually. I'll move it down just in case. Bunch of proteins, we run the current, and they're going to sort based on their isoelectric points, as we said before, right? Just like how, let's say they're in a low pH, right? For them, let's say they're in the middle, and let's say it's too low for them, and they're positively charged. Well, they're going to move to the right, right? And at a certain point, right, because we're going higher in pH, we're going to get to our Zwitter ion eventually. And when it gets neutral, right? Let's say it gets neutral right here. Here, let's say it gives up its carboxylic H plus. Or it doesn't have to be carboxylic H plus. It just gives up an H plus, right? And then it becomes neutral. It's going to stop there. It's going to stop migrating because there's no, reason for it to move, right? It's neutral. It's neutrally charged. And so then the protein's there. That's great. And likewise for a protein here, let's say a protein in the middle is negatively charged, right? Its pH is too high there. So if it's negatively charged, it's going to go towards the positive anode, right? And likewise, eventually, it's going to get to a pH where it'll take back an H, an H plus, right? And that will neutralize its charge, and it'll stop, let's say, at like pH 4, all right? That's sort of the logic of how this works. And then afterwards, we have to wash our amphilites, right? Because if we were to dye everything, you might just dye the amphilites as well, and then everything's just blue. So we actually use trichloroacetic acid. There's some other washes too, but we just do that to wash out all the amphilites, but it keeps the protein, so we can still see what the proteins are. And then we can use dyes, right? Beryllium blue is a common dye to just dye the proteins. We can also use indicators to see like at what pH each each segment is. Or we can also use like a protein ladder, if you will, but like a ladder for pH or isoelectric points, where you can have a bunch of proteins of known like isoelectric points, and you put them in there, and then you can compare them after. It's also pretty common. So let's take a look at some results actually. And in this case, they did use a protein. I can't call them a protein ladder. They have a bunch of isoelectric markers where they have known isoelectric points, and then they have sorted the proteins. See, these proteins have a much higher isoelectric point than, let's say, this protein, right? This protein has a very similar isoelectric point to glycine, actually. And yeah, we can see how it's actually very neatly sorted these, and these bands are also very, very narrow. So that's also a nice part of isoelectric focusing, is that you can actually get a pretty accurate. Since in normal page, right, you also have diffusion counteracting your current, whereas in here, I mean, still diffusion to some extent, but it's a lot more clean, since you can run it for a while and really just get the proteins where they want to be. And so let's take a look at some more uses. So obviously, we talked about phosphorylation. Let's link it back, right? If we have a protein A that's negatively charged, right, and we have our acrylamide, like let's say this is our map. Let's say this is low pH and this is high pH. This phosphorylated one, right, since it's more negatively charged, right, it's going to want to go more towards the positive anode, right? So it might be over here, whereas the normal protein might just be here. And now let's say we use like a phosphatase, right, to break this phosphate ion off. And let's say this band, right, when we run it again, ends up there, and this band disappears. We can be sure they're the same protein, or at least relatively sure, right? So that's one way of one use of isoelectric focusing. Also isoforms, right? These are just charge variants of the same proteins, right? If you have a family of proteins that just vary in charges, this is one way to differentiate them, right? And there's also a really cool technique called two-dimensional page, where we actually do isoelectric focusing first, right? Like imagine we did isoelectric focusing like this, and imagine this is the top, right? Imagine this is it, like this thing is like here, right? This is like here, and then we have like, right, whatever, right? We can actually have a two-dimensional gel and run SDS page on this, but downwards, right? So in this case, we would have the negative anode up here, positive cathode down here, and then run this, right? Positive anode, negative cathode, right? And then we would run it, and we then actually get, like, let's say this guy was here, this guy was here, whatever. We now get a two-dimensional array of these proteins that are sorted by both size, right? Remember, SDS page sorted it by size, and by isoelectric point, which is more or less charge, right? And now we have a lot of data, and this is actually a very good way to find differences in proteins and classify different proteins. Let's say you took a bunch of proteins from a cell and you want just to sort them and differentiate which one is which. And obviously there's a lot of data for proteins, right? So you can actually match proteins pretty well using that method, because you get a lot of information. But yeah, those are probably the uses of isoelectric focusing. I'm not an expert in electrophysics or very advanced biochemistry, so I can't say too much of the nitty gritty here, but that's sort of the overview of what isoelectric focusing really is.